Okay, welcome to the third session from the second chapter, computer networks. Last session we discussed about the encoding NRZ, NRZI, master 4B, 5B and the framing. So the next topic here is the error detecting. Error detecting, it's very important. Here we have a CRC problem, checksum problem. These problems are very important. So what is the error? First we have to understand what is an error means. So suppose we are transferring the data 10001. So while transmitting in the channel, due to the some thermal noise, some electrical noise, a bit may be changed. 1001 is the data means 1101 it will be received at the receiver side. So this error may be because of a many reasons, because of a electrical interface or thermal noise, or there may be a cut off a channel. So there may be many issues may be come for an error. So this error has to be detected and the receiver has to decide whether this is the correct data, whether it will accept, or if it is an error is found, that it will be discarded. So this is an error and it has to be detected for a data has to be in a clear way. So there are three ways: two-dimensional CRC, cyclic redundancy check, and the checksum. This one is very important, definite 10 marks question. Okay, so two-dimensional parity. Before the two-dimensional parity, you have to understand a one-dimensional parity. So in a one-dimensional parity, there are two methods: odd parity and an even parity. So what it is, for any data will be there. For that data, extra bit will be added at the end. Okay, at the receiver side also it will be detected if the same error is received or not. So how? So add parity, this is our actual data. Let's assume this is our actual data 0101011. Okay, so odd parity means here we will count the odd number of ones. Odd number of ones. We have to make sure that data is it should contain a odd one number. So here see how many ones are there: 1, 2, 3, 4. 4 ones are there, which is a even. But we are in the odd parity. To make it as a odd, I will add the extra 1 at the as a parity bit. This one is called as the parity bit. So with the actual data, we will send the parity bit to the receiver. See 0110111. How many ones are there? 1, 2, 3, 4, 5. So we made an odd number of ones. So at the receiver side also it will check 0. At the receiver side what it will check? 01011 with the parity of a 1. It will check how many number of ones are there. 1, 2, 3, 4, 5. So 5 bits are there. So there is a no error, it will be accepted. Suppose there is an error. Suppose this 1 becomes a 0 while transferring. Okay. So at receiver side it will becomes a 0. It will count how many ones are there. 1, 2, 3, 4. 4 ones are there, which is not acceptable. Why? We are in the odd parity. So when there is an even number of ones, it will be discarded in an odd parity. Okay, so even parity in the reverse way, even number of ones we will see. Even number of ones. So suppose this is the same data 0101011. So how many number of ones are there? 1, 2, 3, 4. 4 numbers are there. So what we have to do? So to make it as even, I will add the extra 0 as the even parity. 1, 2, 3, 4. So 4 number of ones are there. So this will be transferred to the receiver side. So if the same number of data it is received means it will be accepted. Again, if there is a vary in the number of ones, it will be discarded. As we are done in here, it will be discarded. Okay, so this is a one-dimensional array. So based on this one-dimensional array, so what's the drawback of this one now? For every frame we have to construct. Suppose this is a one, we consider it as a one of the frame. Here we have to add, here we have to add. But for when we are sending a huge number of data, we require a huge number of error detecting technique has to be done. So that's why they combined the different frames. See, this is a one frame. This is the one frame. They combine the different frames and they will do the two dimensional. So from the row wise and from the column wise, both the wise the number of ones will be counted and it will be forwarded. So this will be for a collection of frames. So here we let's see in a row wise how many ones are there. 1, 2, 3. 3 ones are there. To make it as a even, I will add a 1. So even parity we are doing. 1, 2, 3. 3 ones. To make it as even, 1 we have added. So 1, 2, 3, 4, 0. 1, 2, 3, 4, 5, 1. Similarly 1, 2, 3, 1. So here also we will check 1, 2, 3. 1, 1, 2, 3, 1, 1, 2, 3, 1, 1, 2, 3, 4, 5, 1, 1, 2, 3, 4, 0, 1, 2, 3, 1, 1, 2, 3, 1. So these are all the parity bits. See here, these are all the extra parity bits that will be sent. Parity bits. So at the receiver side also it will cross verify how many number of ones are there. So in this case only particular frame can be rejected. Okay, if this is a mismatch, this will be rejected, and if there is a mismatch, this frame will be detected. So here the first setup it is to at both the sender and the receiver has to come to that commitment like a agreement. So if you are doing a one dimensional, the receiver should also do the one dimensional. If you are doing a two dimensional, the receiver should also do the two dimensional. And main thing, even parity and the odd parity. See at the sender side, if you send the even parity, but the receiver side it will check for the odd parity. Of course there will be a mismatch will be there, the frame may be completely rejected. So at the before transmission, while doing the setup only, with the receiver and the sender, they will come to an agreement which kind of a check they are doing. Okay, this is the two-dimensional parity. Okay, the second one is the cyclic redundancy check, very important. So here also we will add the extra bit at the sender and the receiver side. So it will be cross verified at the receiver side. So this one it will be used in a framing method of HDLC and DDLC, that the previous session we have discussed now. This framing technique they will add this CRC while doing the framing, while sending the data. They will add the extra CRC and they will send. So what is that CRC we are adding? That is the point here. So this cyclic redundancy check. So before doing that, simple first one it will follow the some polynomial technique. Polynomial technique means how the number data is represented here to the power x to the power of 6 plus x to the power of 5 plus x to the power of 4 plus 3 plus 2 plus x to the power of 1 plus x to the power of 0. Like this the data is represented. But how we can understand in the form of a ones and zeros? That is an interesting one. See, suppose our data is 1, our data 1 0 0 0 0 1 1. Suppose this is our data is there. So how we can represent it in a polynomial style? in a polynomial style. So this one 1 into x to the power of 0 plus this one 1 into x to the power of 1 plus 0 into x to the power of 2. So this will be x to the power of 3, this will be x to the power of 4, this will be x to the power of 5, and this will be 1 into x to the power of 6. Okay, this 0 part I skip here. So 1 into x to the power of 6 means what? It will be the x to the power of 6. So 0 into x to the power of thing that those are will become 0, 0, 0, 0. 1 into x to the power of 1. So this one I write it as the x. Plus 1 into x to the power of 0 means nothing but 1. X to the power of 0 is always be 1. So this is the how the data is represented in a polynomial. If they are given in the polynomial style, you have to write it in the bitwise form. So I will write one more example. Suppose the in a polynomial style, if they are given polynomial style x to the power of 4 plus x to the power of 1 plus 1 if they are given. So what is our data in a bitwise? Data in a bitwise. So directly we can write x to the power of 4 is there, I will write it as 1. X to the power of 3 is not there, I will write it as 0. X to the power of 3, x to the power of 2 is not there, I will write it as the 0. X to the power of 1 is there, I will write it as 1, and here last bit 1 is there, this is becomes the 1. See, cross verify. X to the power of 1 into x to the power of 0, 1 into x to the power of 1, 0 into x to the power of 2, 0 into x to the power of 3, and 1 into x to the power of 4. This will becomes 1, 0, 0, 1, 1. Right? The both the way you have to write it in a way. If they are given in the data wise, you have to write it in the polynomial. If they are given in the polynomial style, you have to represent it in a bit form. So this one is a very tricky and interesting also. So but how it is implemented in our problem, that is the question. So here one more thing, the highest degree of a data, see here, let's take this one. What is the highest degree? 4 is the highest degree of this data. This one 4 is called as the degree of this polynomial. Degree of polynomial. Okay, in this one which is the highest degree? 6 is the highest degree because 6 is the degree of this complete data, complete polynomial. 6 is the degree of polynomial. Okay, this is the thing, degree of the polynomial form. Okay, now the actual detection, how we will see how the question will be asked now. We will solve with a simple one. Example 1. The data they are given in the bit stream. The data is 0, 1, 1, 1. This one we call it as the message m of x, and the generator, they will be given generator is 1, 0, 1, 1. This one we call it as the g of x. So now the first step, we have to take the degree of a generator. Degree of generator is what? Degree of g of x 1, 0, 1, 1. How I can write? X to the power of 4 plus x to the power of 3, x to the power of, sorry, this will be x to the power of 3, and x to the power of 1 plus x to the power of 0. So what is the degree? So 3 is the degree. 3 is the degree of the polynomial. Now this generator, we will divide this generator with the data by adding this 3 extra zeros. So observe here, what is our data? Data here it is a 0, 1, 1, 1. We will add the extra parity bit as a 0. How many extra bit we have to add? That one is mentioned here. See, the degree of a generator is there given it as a 3. We will add the extra 3 zeros here. This data is divided with the generator 1011. Okay, 1011. And how it is divided? Based on the XOR technique or the modulo 2 technique also you can use. What is the XOR? When 0 0 is there, 0 0 1 1 1 0 1 1 1 0. So this is the XOR technique. Now coming to here, we have to divide here. See, initial it is in the data 0 is there. While doing the division, if you remember, we has to remove this most significant bit. This left side bit we have to remove. So this one we have to remove. So if it is 0 is there, we will divide the data with a 0. So 1 into 0, 0, 0 into 0, 1 into 0, 0, 1 into 0, 0. Okay, so now we're doing the exam. This 0 0 1 0 1 0 is 1 1 0 is 1 1 0 is 1. So as the basic division, this data will be removed and we will take the next bit below. Okay, so now the first bit is 1. We have to remove this 1. So if I divide multiply this one with the 1, this will be removed. See, 1 1s are 1 1 0s are 0 1 1s are 1 1 1s are 1. Similarly, XOR 1 1 is 0, 1 0 is 1 1 1 is 0 0 1 is 1. So this bit is removed. The next data will be taken below the 0. So this bit we have to remove here. So if I multiply this by 1, it will be removed. So 1 0 1 1. Similarly 1 1 0 0 0 1 1 1 1 is 0 0 1 is 1. So this bit will be removed. So taking the next parity bit below 0. So 0 is there, we have to remove this 0, we will divide it by the 0 itself. So 0 0 0 0 0 0 0 1 0 1 0 0. So as a basic division, this will be removed. See, this is our extra parity bit. So what's the data we will be transferred? That is a transferable data is the original data. The original data here is the 0 1 1 1 plus the parity bit. That is a parity 0 1 0. This one it will be removed. At the receiver side also we have to do the same calculation. If there is any mismatch, it will be discarded, or if it is the same, it will be accepted. So this one it will be at the sender side. What is the data we have sent? This is the data. So at the receiver side also same method. Receiver side, what is the data we have received? T of x is 0 1 1 1 0 1 0. Okay, so this data is divided with the same generator 0 1 1 1 0 1 0, and the generator value they have given 1 0 1 1. So same XOR method. So initial 0 is there, we will take a 0 0 0 0 0. So 0 1 0 1 1 0 1 1 0 1. This 0 will be removed, taking the 0 below 1 1 0 1 1 1 1 0 1 0 1. So this 0 will be removed, taking the 1 below. So 1 1 0 1 1. So 0 0 0 0. So this will be removed. Taking the next bit below, 0 0 0 0 0 0. So here when we receive all zeros in a calculation as reminder, that means no error. Okay, so if we receive all zeros here at the receiver side while calculating, that means there is a no error and we can accept the data. But while calculation, if there is a error here, we have to discard that data. So how they will mention, suppose there is a error at the second bit, third bit, error, detect the error, suppose they will be asked. So in that case, suppose there is error at second bit. When transferring, there is a error at a second bit. Detect how the error is detected at the receiver side. So actual data what we have received, it is a 0 1 1 1 0 1 0, but they are telling that there is a error at the second bit. So error means 0 will become 1, becomes 0, 0 becomes 1, and remaining all will be the same. 0 1 1 0 1 0. This is the error bit we have to detect. Okay, so how it will be detected? That is also same calculation. So what it is received? 0 0 1 1 0 1 0. And what is the generator they are given? 1 0 1 1 1 0 1 1. See, error is at the second bit. This one we have to identify. So same method with a 0 0 0 0 0 0 0 1 1. This will be discarded. Taking the next here 0 0 0 0 0 0 0 1 1 0. This will be removed. Taking the next one here 1. See, 1 is there, we have to remove here. That way we will multiply with the 1 1 1 0 1 1 1 1 0 is removed. 1 1 0. So taking the second last bit here, 0 1 is there, 1 1 0 1 1 1 1 0 1 1 1. See, here we are not received all 0. So this means that error is there, so the data will be discarded. If we receive all zeros, then there will be a no error. If we receive at least any one in the receiver, that will be discarded. It's the simple problem in a CRC. But how they will ask in a exam? There is a question. Okay, so a bit stream. The bit stream, the data is 1. This is the data. The data 1 1 0 1 0 1 2 3 4 5. Okay, the data is using the standard CRC method. The generator polynomial here is g of x. They are given it as the x to the power of 4 plus x plus 1. Show the actual bit string transmitted Due to noise, the least significant bit is inverted during the transmission. Show the bit string received and the error is detected at the receiver side. So first we have to detect what's the data actually it is sent. So how you write this one? 1 into x to the power of 4 plus 0 into x to the power of 3 plus 0 into x to the power of 2 plus 1 into x to the power of 1 plus 1 into x to the power of 0. Okay, so what is the data? 1 0 0 1 1. So this is the g of x. So what is the degree? The highest degree of the g of x is 4. So these 4 zeros will be added at the as a parity in a data. So the data here is 1 0. So 1 1 0 1 0 1 2 3 4 5 5 ones 1 2 3 4 5 and the extra 4 zeros which is here 1 2 3 4. Okay, and this will be divided with the generator 1 0 0 1 1. Okay, so simple calculation. We are using the XOR method. 1 1 is there. We'll take a 1 1 0 0 1 1 1 1 0 1 0 1 0 0 1 1 0 0 1 1. So at any cost we have to remove this one. So left bit has to be removed. Based on that we have to choose the divisor. So 1 is there. Again next okay, taking the 1 below 1 1 0 0 1 1. Okay, 0 0 0 0 0. So this bit will be removed. Taking the 1 below here. What is this? 0 1 2 3 4 5 0. It will be removed. 0 0 0 1. Taking the next, the division will take a longer time. So we'll come to the okay. After calculation, then what the receive reminder will be 0 0 1 0. So what's the actual data that is transmitted? The t of x that is transmitted here is the original data 1 1 0 1 0 1 2 3 4 5 1 2 3 4 5 followed by 4 zeros. So instead of 4 zeros, what's the reminder we got? 0 0 1 0. This will be, it will be transferred to the receiver side. So but they are continuing with the question. Due to noise, the least significant bit is inverted during the transmission. Show the bit string is received. So here at what is the actual data till here? This is the actual data. Till here it is the actual data. So MSB more significant bit and the LSB least significant bits from this side. So they are telling this data is inverted. So what the actual data that he received? 1 1 0 1 0 1 2 3 4. Fifth bit is inverted. Fifth bit is inverted. So this is the error we have to detect at the receiver side and 0 0 1 0. So this is the at the receiver side we have to calculate and we have to detect it. See at the receiver side they are telling least bit is an error. So this is an error. After the calculation, this is the reminder we got. This is a all not zeros. So we conclude note that there is an error. Therefore, we discard the data. Discard the frame. Okay. So this is a definite 10 marks question. So the steps I will repeat. The data they will given and the generator they will be given, and we have to frame the what is the data that is transmitted. So here with the g of x, that is the generator they have given, this one we have to represent in the form of a bit form. So this is the technique we have to convert. So what is the degree of a g of x? The highest degree will becomes the degree of that polynomial. Here the highest degree is 4. That is the degree of g of x is 4. This extra 4 bit we will add to our original data. This will the parity bit. So what should be the parity bit? That one we have to calculate. So this one we will divide with the given generator 10011. So we have to remove this more significant bit as a simple division. So we will check with the first bit. If 1 is there, take a 1 and do the calculation. 1 say 1011. So this will be removed. If the 0 comes, means we have to take a 0 and we have to remove the more significant bit. So at the what the remainder we will got now 0010.